So I'm going to start with a quick video on significant figures and why they are important. Additionally, I'm also going to talk a little bit about accuracy and precision because they are the concepts, while we think of them a lot in the same way, they really aren't. So let's start with significant figures. First of all, numbers have meaning. If I were to give you a list of numbers, such as the number 7, 365, 30, 60, to 3.14, or 27, I've just given you a list of numbers. But most of the time you think about those numbers, like if I give you 7, you might immediately think of 7 days in a week. Or 365, you might think of 365 days in a year. Now 30 and 60 might have a variety of meanings. For example, it could be 60 minutes in an hour. It could be 60 seconds in a minute. 30 could be the number of days in a month. But those are all different numbers. Now, one of the numbers I gave you was a little strange. I gave you the number 27. I used 27 because 27 in physics is a number that we're going to use a lot, but we don't typically think about 27. 27 meters per second is very, very close to 60 miles per hour. We know what 60 miles per hour is, but we don't necessarily know what 27 meters per second is. So, numbers have units. Now, sometimes those units are not what we think about. For example, 15 could be 15 apples, or 12 could be a dozen eggs, or 12 could be the numbers around the clock. Those numbers, we want to specify what they exactly have, those meaningful pieces. We want to get that in there. And that's where the significant figures comes in, because significant figures tell us the precision of the instrument that we're using. For example, I might have a scale at the grocery store. And since we're in chemistry, let's think of the grocery store being in the European Union. And if I go and look at a scale, that scale is going to be in kilograms. And my scale in the grocery store is going to be weighing 1 kilo of apples or 1 kilo of oranges. And so I'm going to be looking at that particular significance or precision in my measurement. When you're in the laboratory in chemistry, we're usually going to use a digital scale, or you might use a scale that's a triple beam balance. And in that first instance, that scale is going to be measured in like 0.001, where we're looking at 1,000th of a gram. Very, very different precision. And you can think about what this makes sense. For example, if I'm measuring the distance between two cities, I'm not going to go take a ruler that's 12 inches or 30 centimeters. I'm not going to go take that ruler and measure the distance between the two cities by using a ruler. I'm going to use a different type of measurement device that's going to allow that distance to be measured easier in kilometers. So we will pick our instrument for the precision that we need. I don't need to know the distance between Ponca City or Tonkawa, or the distance between Tonkawa and Oklahoma City to the 1,000th of a meter. If I'm close enough to a meter, that's probably sufficient. So that makes the difference when we're talking precision. Precision is related to the instrument that we're using, and that makes a huge difference. But when we're counting significant figures and how we write significant figures, the first rule of thumb is scientific notation is going to give us the best identification of significant figures. So if I write 1.23 times 10 to the minus 4, I know that I only have 3 significant figures. 1 in the ones column, the 0.2 in the tenths column, and 3 in the thousandths or in the hundredths column. So those are going to give us the number of significant figures. So let's look at these examples. These zeros here are placeholders. If I were to write this in scientific notation, this would be 3.5 times 10 to the minus 3. And that will tell me definitely that I have two significant figures. Those zeros are just telling us where the digit is. They're placeholders. This digit, on the other hand, this zero in this number is significant. Because if I were to write this in scientific notation, this would be 1.230 times 10 to the minus 1. That zero is significant, and it is over here, and it is telling us something. Now, the interesting thing, your calculator won't do significant figures because it's going to drop that zero. You're going to have to watch for those significant figures. If I have a number that looks like this, 12,300, those two zeros there are just placeholders. If I'm going to write this, it's going to be 1.23 times 10 to the third. And those zeros aren't significant, but I can make those zeros significant by either doing this as 1.2300 times 10 to the third. If I'm doing that in my scientific notation, I've actually represented those zeros as significant, or I can put a decimal point there. And that tells me that those zeros are actually real. And that's not just my precision of my instrument. This number, if I have a zero that's between two non-zero numbers, that zero is significant. There's where I'm representing that zero as being significant because I've put that decimal point there. But remember, scientific notation is always going to show you how many significant figures there are. And then if I have this in scientific notation, you can see that. If I have an exact number, like 15 apples, those actually have infinite number of significant figures because it is that particular one. It is measured to that exact number. Now, rules, we're working with significant numbers. All non-digit, zero digits are generally significant. They are significant. Zeros between non-zero digits are significant, like the 0 in the 504. Exact numbers have infinite number of significant figures. And when adding and subtracting significant figures, you are dealing with the least significant digit determines the position of the result. So if I'm adding 15 and then I'm adding 1.23, my answer is going to be 16 because that last digit, that digit tells you where the error in your measurement is going to be. So we have to really watch that. So I would like you to refer you to your book. You can look in your chapter and see some more about significant figures there and have some examples about how to deal with those. You do have some homework assignments that will be working with that. Additionally, when you're multiplying or dividing, the result reported has the same number of significant figures as the lowest number of significant figures. So if I'm taking 12, which has two significant figures, and I'm multiplying it by 121, my answer is still only going to be in two significant figures because I'm dealing with that multiplication. So some examples here. So let's look at some examples. So these are working with significant figures. You still have your rules here. So going into that addition, if I do 32.4 and I add 36.78, and the result here's, but I'm actually going to report this as 69.2 because this is the number that is going to control the addition or subtraction. Same with this one here. We would actually round this because this is the number that controls how we're adding or subtracting. Another example in multiplication and division, you can see that as well. Now, as you get into chemistry, we're going to be dealing with different instruments, and accuracy and precision are totally different. They are the same, but different kind of things. So let's look at accuracy and precision. So think of a group of pennies, and I'm going to move myself over so that I'm not blocking the screen. But I have a set of pennies. Now, interesting thing about pennies is if you take 10 pennies and you weigh them, and you can take 100 pennies and you weigh them, you're going to get a range of pennies that are going to be between 2.356 and say 2.534. Somewhere around, you'll get a nice distribution around 2.500. That is very important because a penny fresh from the mint is going to weigh 2.500 grams. So if I weigh 1 penny here, I got on my little handy dandy miniature scale, I have 2.49. Now this particular scale does not go to that third significant figure. If I'm in the chemistry laboratory, I probably have a scale that will go to that third significant figure. But this scale is going to give me 3 significant figures. So 1 penny is 2.49 grams. Now in this one, I have weighed out 10 pennies. In this case, I've got 25.01 grams. So the average penny is, if I divide that one by 10, 10 is an exact number. There are exactly 10 pennies. So if I take my 10 and I divide that by my 25.01, I'm going to get a number that says 2.501 because I'm dividing by an exact number. Now, the instrument here really can only measure to that 10th significant figure. So you can see a lot of people that would say, nope, my answer needs to be 2.50 because that is where I'm at with my pennies. And if I were adding those pennies, that's exactly how I would do it and get there. But my dividing by my number, so you should be able to get your 4 significant figures. Now, the interesting thing is if you take 100 pennies, your average really is going to come out to be something more like 2.52 for 1 penny. In fact, there's a built-in bias. Now, you can think of bias in a measurement as somebody putting their thumb on the scale. Many of us have a bathroom scale. If it's the old mechanical design, you know that that bathroom scale, somebody may have adjusted it to be 5 pounds heavier so that you don't panic when you go to the doctor's office and their scale is different. But that puts a bias in the measurement. That thumb on the scale at the grocer or that thumb on the scale at the meat market puts a bias. Well, it turns out Mother Nature can be biased. If I have 100 pennies and I go out there and I measure 100 pennies, now when I say the 2.500 grams per penny from the mint, those are from pennies that are past the date of 1984. That's when they changed the composition of pennies, and pennies prior to 1984 had a different mass. So we want to be able to do that. So that's a good thing. Now, I just used 2 different words, mass and weight. Weight is actually a force. Weight is how mass reacts to gravity. And so we use in chemistry and in a lot of things, we use weight and mass kind of interchangeably, because if I put the pennies on the scale is actually taking into account for gravity, and it's actually providing you with the mass. So weight will be in pounds if I'm in there. Weight will be in newtons if I'm in SI units. So we are actually talking about mass here, and we'll talk a little bit more about what mass is as we go through this course. So mass is the amount of stuff that we have. Weight is how gravity acts on that stuff. So, but we're going back to the bias situation. Well, it turns out that pennies in circulation are going to gain mass because they're going to oxidize. So that penny is going to actually get more oxygen associated with it. So pennies in circulation are going to be biased because over time the pennies are going to oxidize and they should gain mass. So if I look at a distribution of pennies that have been in circulation, my actual mean or average penny is going to have slightly more mass than what it came from the mint. So that gives us a good explanation of bias. But let's talk about precision and accuracy. Now, precision, again, is related to my instrument. Am I using a ruler? Am I using a yardstick? Am I using, a tape measure that's measured out in feet? That's going to tell me how precise my measurement is. So if I look at it and think of a bullseye, accurate and precise would be a tight grouping around the actual center or the target number that I'm looking for. This one says I'm very precise. My instrument gives me that precise reading, but it's not very accurate. It's nowhere close to what the actual number is, or it's nowhere close to the center of the target. This case, we've got a wide distribution, very poor precision, but we're not accurate either. We're not getting it. But if I look at this one, I'm not very precise, but when I take the average of those 4 measurements, I'm going to likely hit dead center and be very close to the number. So accuracy is different than precision, and we have to worry about bias. Bias is important. Bias can be built into the measurement, which is a lot of reasons why if you go to the gas station and you'll see on the pump, it'll say R plus M divided by 2. One is the research method for determining octane, and one is the measurement method for determining octane. The 2 methods will give you slightly different answer, but we use the average of the 2 methods to rate the octane on the gasoline at the pump. Same with cetane for diesel fuel. So we do look at accuracy, we do look at precision, we want to look at bias. And that will get us into percent error. Percent error is looking at how close did your answer come to what the known value is. So we have a lot of standards that are out there. And if I took a standard mass and put it on the scale, and I'm looking at how my scale measures that mass, I'm going to look at the percent error. That's very different than the percent difference. And the percent difference comes in looking at 2 different methodologies. I may look at measuring using a laser guided measurement device like you see a surveyor use, versus looking at my car to measure the distance following my odometer on my car. Those 2 measurements may be very precise for the instrument that I'm using, but I'm going to get a slightly different answer because those 2 instruments aren't the same, nor do they have the same precision. So I might want to do percent difference. So I encourage you to read the sections in your book, look at accuracy, precision, and bias, and look at those examples for using significant figures. Hopefully this will help you in this particular area, and you can come back to this video anytime.